Good evening, everyone. I'm Professor Andrei Zvelindovsky from sunny Lincoln, and we have this Astro-Chat with our distinguished guest, Professor Don Kurtz. I'm sitting in Lincoln, at the University of Lincoln, and Don Kurtz sitting in South Africa. With help of technology, we can chat tonight about various exciting astronomical things. Before we proceed with our program, I just encourage everyone who join us, and I see lots of people from various places joined already us in the live chat, to push a like button, and also you can subscribe to our channel. That will help to more people in the world see this video due to YouTube algorithm. And I see people join as far as San Diego now. Good day to good evening, good morning, good afternoon to everyone who joined us tonight. This is our 21st Astro-Chat with Don, and therefore I will not introduce Don for 21st time. However, if you happen to be for first time with our Astro-Chat, you can read description of our Astro-Chat as well as Don's bio in the link where description of this video is. And I also tell you that after Astro-Chat will be finished, after Don finished his presentation, you will have time to ask him directly questions by typing them inside of live chat. And with that, I give floor to Don. Welcome, Don.
Hey, thank you for the introduction, Andrei, and good morning, good afternoon, good evening to everyone. You know, astronomy is different from other sciences. In physics, chemistry, archaeology, biology, one can do experiments. You can manipulate the conditions and see what changes. In astronomy, we cannot manipulate the universe. All we can do is observe it. And tonight's talk, I want to talk about how our ability to observe, mostly in the optical part of the spectrum and from the ground, has utterly revolutionized the way we see the universe over the 400 plus years since we first discovered how to make a telescope. Now, let me pause briefly here while I share my presentation with you. We'll move to the slideshow. And I have entitled it Big Glass, the Giant Telescopes, because that's where we're going by the end of the talk. In the early 1600s, a man named Hans Lippershey, or Lippershey, the spelling varies, living in the Netherlands, first applied for a patent for a refracting telescope. And you'll see on there what he said. It was for seeing things far away as if they were near. Another Dutchman, Jacob Metius, made a similar application just a few weeks later. It's clear that the idea for telescopes was in the air. It's possible other people had already experimented with this. Lippershey gets the credit for invention of the telescope because he's the first one who applied for a patent. There is a story that he got the idea because he saw a couple of boys in his shop. He was a spectacle maker, and a couple of boys were holding up lenses at different arms length and actually making themselves a telescope so they could see things that were far away as if they were nearby, and that gave Hans the idea to make a telescope. In any case, by the next year, that telescope had been moved to viewing the sky. Now, Lippershey has got an award, or if you like, a memorial from astronomers. We've named a small crater 7 kilometers across on the moon, the Lippershey crater. It was Galileo who, at least in recorded history, was the first to turn one of these new telescopes on the sky. Now, there's a painting of Galileo, very, very famous in his lifetime and ever since for many things. And on the right are two of his original telescopes that are in the Galileo Museum in Florence. They're small, they're handheld, but with them, he could see what no human had ever seen before. In 1609, he first turned a telescope on the sky. The telescope had an aperture of 37 millimeters, so the lens was round, and the 37 millimeters was the diameter of that lens. Most of you have probably got binoculars, and if you've got binoculars that are, say, 10 by 50 binoculars, that 50 means that the aperture of your binoculars is 50 millimeters, bigger than Galileo's telescope. The 10 is just the magnification. His telescope could magnify about 30 times. He discovered mountains on the moon. Humans had never seen those before. He found spots on the sun, which showed that the sun was not perfectly smooth and regular. And furthermore, he watched the spots move so he could see that the sun was rotating. He found the 4 largest moons of Jupiter, which we call the Galilean moons. He discovered phases of Venus. Venus has phases that the moon does, and the fact that it has phases proved that Venus orbits the sun. He at first just discovered little bumps on the image of Saturn with his original telescope, which didn't have much resolution, but eventually resolved them into rings, around Saturn. And of course, he saw more stars than any human had ever seen before him by turning this telescope on the sky. So here from 2015 is an ensemble of images of Venus over 6 months. And what you're looking at, there's my red cursor here. In the background there, when Venus looks small and full, it's on the far side of the sun, where it's much further from us, so it appears smaller, and the sun lights up the face that we see. And then as Venus orbits the sun with respect to us and gets closer and closer, eventually, when it almost passes between the sun and us, the sun's lighting up the other side, and only a sliver of a crescent Venus shows. And of course, because Venus is then between the Earth and the sun, it's much bigger in the sky. So this observation of Galileo proved that Venus orbited the sun. Here's an image of Jupiter that I took from the Stellarium program. This is for the beginning of this month. Jupiter's a bit too close to the sun to be observing now, but it shows Jupiter with its 4 satellites that were discovered by Galileo. This image with the Stellarium program is actually better than Galileo would have been able to see. The program will nicely label them for you. Those 4 satellites he found were Io, Europa, Ganymede, and the farthest one out here, Callisto. 2 more of the smaller satellites are labeled in this picture. So Galileo also showed with his telescope that objects orbited Jupiter, and of course the dogma at that time was that everything orbited the Earth, and clearly from his observations Venus didn't orbit the Earth and the moons of Jupiter didn't. Where have we gone since that first telescope was turned onto Jupiter a little over 400 years ago? Well, the European Space Agency now has a mission on the way to Jupiter. It's called the Jupiter Icy Moons Explorer. It'll arrive at Jupiter in July of 2031. There's an artist's impression of what the satellite looks like, and it's going to explore primarily those icy moons, Europa and Callisto, Ganymede, Europa, and Callisto, that Galileo discovered. The US NASA has also launched a satellite out to Jupiter. It will arrive at Europa, the second of those moons, to study its icy surface in 2030. And that's a reconnaissance for eventually going to land on Europa, melt down through the ice, and go explore the oceans of Europa. What an amazing distance we've come in 4 centuries from Galileo's first look through a small telescope to discover those 4 moons of Jupiter. Now, telescopes come in 2 main types. I'm talking about optical telescopes, radio telescopes and X-ray telescopes, that sort of thing. We'll wait for a future Astro-Chat. The optical telescopes come in 2 types, refractors and reflectors. And there are 3 main things we're concerned with. As astronomers, actually 2 major things. I've thrown in the 3rd one because it'll be of interest to you. We're primarily interested in the light gathering power of the telescope. That's how much light it can capture, because the light's carrying the information. The more we capture, the more information we get. In terms of looking with your eye, the more light we capture, the brighter something seems. And so the farther away we can look more deeply into the universe if we can capture more light. That needs a bigger telescope. The other thing a bigger telescope gives is it gives us better resolution. Our ability to see finer detail comes with larger telescopes. And so our drive to build ever bigger telescopes are primarily to gather more light, to see farther, to see more clearly, to see more brightly, and to get better resolution to see more detail. We can manipulate the lenses and the optics in the telescope to govern the magnification, and so that is one of the characteristics of these telescopes, but that's under our control in the design of the telescope. A refractor uses a focusing lens. Over here on the left, there's a convex lens. The light comes in. The light is refracted, it's bent, it comes to a focus where a real image of the object in the sky appears in space there. And then we use another lens, usually convex, but also can be concave. We use that as a magnifying glass to look at the real image that's been formed by the objective lens. That's the way that a refractor works. The magnification is just dependent on the relative focal lengths of the two lenses. And as I said, we have control over that. The amount of light gathered depends on the size of this lens that captures the light, and the resolution also depends on that size. And so here is the crux of why we want bigger and bigger telescopes. The aperture of our telescope will be circular in cross-section. The smallest telescope we humans use, if I can call it that, is our own eye. And the aperture of our eye we call the iris, the pupil. And the pupil admits light. Now, our pupils are normally during the day about 3 millimeters in diameter. At nighttime, to gather more light, we've got the ability to become dark adapted, and the pupil will expand to about 5 millimeters, letting in more light, so we can see in darker conditions. So the aperture of the telescopes are characterized by the diameter of the aperture. I've labeled that as D. The radius, of course, is half of that. That's R. The amount of light that the telescope can gather depends on the area of that aperture. And you'll remember from school, or you know well yourself, the area of a circle goes as pi times the radius squared. So if you double the aperture of a telescope, the light gathering power goes up by 4 times. If you make the aperture 10 times bigger, the light gathering power goes up by 100 times. We astronomers seek bigger and bigger telescopes to gather more and more light. We also seek the bigger telescopes because the bigger the aperture, the better the resolution. So on the right here is an image of what should be a point source. This is just an illustration. A star is so far away that it's essentially a perfect mathematical point for most stars. We don't resolve them into their surface. But when the light passes through the telescope, it's diffracted. The wave nature of light as it passes the aperture causes it to be diffracted, and the image is then spread out in what we call a point spread function, which should be a perfect dot gets spread out into a disk, and then the diffraction of light causes interference, which gives us these light echoes or rings. And so what should just be a single point ends up being this rather mess of a blurry spot with lots of rings around it. If we've got a small telescope, two objects which are closer together, as here in the bottom, will not be distinguishable from each other. But as we make the telescope aperture bigger and bigger, we're able to resolve better and better things that are close together. And so that is the second major thing we're seeking when we build bigger and bigger telescopes, better resolution. At the bottom, I've given the actual formula for angular resolution for a telescope. It depends on the wavelength of light. The wavelength of blue light is shorter than red light, and so we can actually get better resolution with blue light than red light. We get better resolution in the optical than we can in the radio region, because radio is very long wavelengths because of this factor. But the resolution goes up. The resolution improves. The angle we can see is smaller and smaller the bigger the diameter of the telescope is. And so radio telescopes, for example, which will be in our next Astro-Chat, we can make those so gigantic that this diameter of the telescope wins, and we can see much finer resolution with radio telescopes than in the optical. This man, George Ellery Hale, is really one of the heroes of astronomical observation and astronomical science and astrophysics. George Ellery Hale, as you'll see from his dates there, was born in the 19th century and lived up until the early parts of the 20th century. And he was an absolute genius. He was driven. He knew how to build. He was an engineer. And he also knew how to play politics and to get funding. He was a close associate and was supported by Andrew Carnegie, at the time probably the wealthiest man in the world. And in the 1890s, George Ellery Hale had discovered magnetic fields and sunspots with his own observations, and he was interested in the physics of astronomy, not just the astronomy of looking to see what can you see, but what is our physical understanding of that. He and one other astronomer founded the Astrophysical Journal in 1895, and it is still the preeminent astrophysical journal in the world, going very strongly now. He was the founder of the Astrophysical Journal. He was a telescope builder. In 1897, he built the world's largest telescope at Yerkes Observatory in Wisconsin. Unfortunately, Yerkes Observatory is on the edge of a lake, and it's very wet there. It's not the world's best observing conditions, but he built a giant 1-meter diameter refractor at Yerkes Observatory. Hale recognized that it would be better to go someplace with a much drier climate and to get higher above sea level, where there's much less moisture in the air, the viewing is much clearer. And he went out to Mount Wilson in California. Mount Wilson is a 1,700-meter mountain that sits above Pasadena on the outskirts of Los Angeles. And there he founded the Mount Wilson Observatory and built another telescope that became the world's largest telescope. And then he built another one that was even bigger than that. And then he made the plans for building an even larger telescope, which moved to Palomar Observatory. We're coming back to these. Now, in Pasadena, there was a small college there called Throop College. It was a polytech. And Hale was on the board with Throop, the founder. And Hale drove that college to specialize in engineering and in physics. And it morphed into Caltech, California Institute of Technology, one of the world's top 10 universities, in some rankings of world universities, #1 in the world. And so he was the fundamental founder of Caltech amongst building all these observatories. He was an amazing man. Here's a picture of the Yerkes 1-meter dome, the dome for the 1-meter telescope being built in the 1890s. You can see how gigantic it is. And the reason for that is that refracting telescopes, here on the right is a wide-angle view of that telescope. It's got a 1-meter, they called it a 40-inch back then, of course, and many of you are in England. I know somebody's at least in California, you understand inches still. 40-inch diameter, we'll call it 1 meter here, which then focused the light all the way down here where the other lens was used to look at the image. You can see the gigantic length of the telescope. Here on the left is just a partial view of it with an observer down at the bottom to give you the scale. This is the biggest refracting telescope that was ever built, and probably nobody will ever attempt to build a bigger one. One of the major problems with building a bigger telescope is that the lens itself cannot support itself and maintain its figure under gravity. Glass is not completely rigid, it's slightly fluid, and it can distort under gravity. And once you get to a 1-meter size lens, as you move it around, point at different places in the sky, the lens is distorted and it's hard to keep the image best. So that was the ultimate in building a refracting telescope. Now, reflecting telescopes were invented very early on. Isaac Newton famously built reflecting telescopes. And there, instead of using a lens, a mirror is used to capture the light. So in this picture, the light's coming in from the right. It hits a concave mirror for a small telescope that will have the shape of a paraboloid. And the good thing about this mirror is you can make it thick so it's strong, and you can support it from behind. So if you make it much, much bigger than the Yerkes telescope, it can be supported against the gravitational stresses as you point it in different points in the sky and keep its figure. The light comes to a focus here called the prime focus. And in some of the world's biggest telescopes that were built, particularly by George Ellery Hale, it was possible for the astronomer to sit in a cage right there at that focal point and ride the telescope for the entire night, doing the astronomy from that prime focus. More usually, another mirror is put in. Isaac Newton put in a flat mirror that would then bounce the light out the side of the telescope where it could be viewed through a high piece. More typically, if any of you have got amateur telescopes, a very common configuration is the configuration we call the Cassegrain focus, after a French clergyman named Laurent Cassegrain from the Collège des Chartres, who in the 1600s invented a telescope which had a secondary mirror that then bounced the light out through a hole in the middle of the other mirror, and then an eyepiece could view through the telescope there. And if you buy yourself an amateur telescope nowadays, most of the good telescopes you can buy need a other ones that are commercially made are typically of the Cassegrain variety. In 1900, here's a list of the world's biggest telescopes. Harvard had a 60-inch, 1.5 meter aperture reflector. George Ellery Hale built another telescope the same size on Mount Wilson, which came into operation in 1908. But other than that, in the turn of that century, all the other telescopes in the world were smaller than that. Here's the Yerkes refractor, but you'll see that the other big telescopes are reflectors. And so come 1900, the drive to build big telescopes was in reflecting telescopes. And here is the 60-inch, the 1.5 meter telescope being taken to the top of Mount Wilson in California. The conditions were extremely primitive. That is the main road to the top of the mountain. And the only way to get the telescope and the equipment up was to pull it up in a mule train with mules pulling the equipment to the top of the mountain. That's how that telescope got up there and was finally made operational. 1908, the world's biggest telescope. And it was unique at the time. And so the world's greatest astronomers flocked to California, came to observe with that telescope. There wasn't anything in the world to compete with it in a beautiful mountaintop condition, in a reasonably dry climate with excellent seeing and a telescope of that size. There's that telescope today. It's now available for anybody to use. You simply have to pay. You or a group of people can rent this telescope for a night and go use it for stargazing and viewing the sky. If you come during the day, you can also do a tour of the observatory and see it without having to pay to use it for nighttime viewing. Hale then built a new world's biggest telescope. He was good at getting money. Joseph Hooker, an industrialist, funded this telescope, 2.5 meter, or as they knew it, 100-inch telescope. This particular picture is from the observatory website for the Mount Wilson Observatory. And so these are their words, where we discovered our place in the universe. And that's not hyperbole. They are correct about that. This man, Edwin Hubble, came to observe with that 2.5 meter, 100-inch telescope. There it is on the right as it looks today, painted up, and it's also used for public observations at a considerable expense, but groups of people do pay to use this, very serious, excited amateurs. And Hubble proved that the so-called spiral nebulae, little fuzzy patches that could be seen through the telescopes that looked like they were in spirals, he proved that they were other galaxies. 1921, there was a great debate between Harlow Shapley of Harvard College Observatory and Heber D. Curtis. Curtis claimed that the spiral nebulae were galaxies like the Milky Way. Shapley claimed that the Milky Way was the entire universe and these spiral nebulae were just clouds of gas in the Milky Way. Hubble began studying the spiral nebulae, and he used a new discovery by a Harvard observer, Henrietta Leavitt, who in 1908 had discovered something called the period luminosity relationship for a kind of star called a Cepheid. It's a star that pulses, it gets bigger and smaller, brighter and dimmer, and she said, it's worthy of notice, the brighter variables have the longer period. It turns out that the big, bright Cepheids have got long periods of pulsation, and the smaller, fainter ones have shorter periods. That was calibrated, and once that was done, all that was needed was the discovery of a Cepheid variable, measuring the time it takes to go through its cycle, which is typically between 1 and 100 days, is easy, even with a small telescope. And that's what Hubble did in 1923. So in this picture in the lower right is Hubble's picture of the great galaxy in Andromeda, the most distant thing you can see with your naked eye, a little over 2 million light years away. At the time Hubble did this, the likes of Harlow Shapley was arguing that this was a cloud inside our own Milky Way. Now, this particular picture was state of the art. That picture would have taken 12 hours of continuous observation with the 2.5 meter telescope, with Hubble sitting up at the prime focus cage throughout the entire night in the cold, with his eye at the eyepiece, looking at a single star and pushing little buttons to keep the telescope tracking perfectly so the image didn't get blurred. And there on the 6th of October, 1923, he's marked up here between those two lines, that little dot, he's marked as variable, exclamation point. He had discovered a Cepheid, and he used that to prove that the Andromeda galaxy was more than 2 million light years away. Overnight, our human view of our place in the universe expanded beyond belief, from thinking that the Milky Way was the entire universe to discovering our Milky Way is just one of, we now know, trillions of galaxies that can be seen with our telescopes in the universe. On the left is a more modern ground-based picture of the Andromeda Galaxy. Compare it to what Hubble could do with the world's best instrumentation only a century ago. And in the upper right is a view of that part of the Andromeda Galaxy, which shows Hubble's star right there with the Hubble Space Telescope. Now, I won't be talking to you about the Hubble Space Telescope or the James Webb Telescope tonight, because I'm talking to you about giant telescopes. And the Hubble telescope is slightly smaller than the telescope that Hubble made this picture with. So Hubble himself made this picture, the 2.5 meter Hooker. Hubble telescope's only 2.4 meters. Its great advantage is it's above the atmosphere. But as you'll hear from me as we get to the end of this talk, we're overcoming the disadvantages of the atmosphere so we can go way beyond the Hubble in terms of resolution with giant telescopes on the ground. Milton Humason is an interesting character. In his teen years, he got a job as a mule skinner at Mount Wilson Observatory. He dropped out of high school at the age of 14. Now, a mule skinner does not skin some poor mule. That's not what that means. In the argot of the day, it was said that mules are very stubborn, and somebody who could outwit a clever mule could skin the mule, meaning they could outsmart it. And so the mule skinner was somebody who could get mules to do what they wanted them to do. And so Humason, at the age of 14, got the job leading those mules up Mount Wilson, carrying the equipment up to build the 2.5 meter telescope. He met a girl on the mountaintop, his age. She was the daughter of the chief engineer, and at the end of his summer, he went back to his family farm in Nevada, but she and he stayed in touch. They fell in love, and they eventually married a few years later. And his new father-in-law, the chief engineer, rather nepotistically got him a job as a janitor cleaning the floors at Mount Wilson Observatory. But Edwin Hubble quickly recognized that Milton Humason was a very smart guy, and being a janitor was not the place for him in the world. And so Humason became a very accomplished observer, made the observations that Hubble used for the discovery of the expansion of the universe. And so here's the paper from 1931 using that 2.5 meter telescope, published in the Astrophysical Journal, which was founded by George Ellery Hale, the velocity-distance relationship amongst the extragalactic nebula, meaning the galaxies. And here's a plot of how fast they're moving away from us. Here's how far away they are. The farther away they are, the faster they're moving. This was the discovery of the Big Bang. Done because we had an ever bigger telescope to see deeper into the universe and to see in more detail. So the goal was to build even bigger telescopes, and George Ellery Hale caused that to happen again. He didn't live to see it completed, but he was the driving force to have the Hale 5-meter telescope, the famous 200-inch telescope, built on a mountain called Palomar Mountain, just about a little bit north of San Diego, where I grew up. This was the world's biggest telescope when I was a child. I was aware of it as a very small child, fascinated by it. When I started astronomy at university in the 1960s, we undergraduates, astronomy students, were taken for a tour of the observatory. And of course, it was a dream to me that one day I might actually get to use this big telescope and look at the sky as a professional astronomer. As it turns out, I never did. But I have used telescopes much bigger than this, and so the dream definitely came true. You'll see the Palomar Observatory itself is also sitting in a rather lush environment with pine trees and grass. It's a decent dry climate, but it's not as dry as we seek out now for our biggest telescopes. We go to the world's driest desert for that. There's the famous 200-inch 5-meter telescope on Palomar Mountain. And of course, when I was an undergraduate, our tour, we were allowed to come in, explore the inside. And the astronomer at the time was a Canadian astronomer, Sidney Vandenberg, who came out and told us what research he was doing and gave us a little bit of insight into what the telescope was being used for. That telescope was instrumental in many of the great discoveries of the middle of the 20th century. Interestingly, A few months ago in March, I was actually lecturing for a private tour company, and our tour started out of Washington, D.C. We went to Iceland, Norway, and Finland, back to Washington. And when I arrived back in Washington, I got a rental car and drove up to Canada to see my relatives in Ontario. And I timed my trip so that I stopped overnight in Corning, New York. And most of you will know Corning from Corning glassware, from Corningware that you would have in your kitchen. Now, Corning Glassworks has been a famous glassmaker for well over a century. And in the 1930s, they were commissioned by George Ellery Hale to pour the mirror blank for this 5-meter, 200-inch telescope. They poured that mirror blank, and because the glass is hot, it has to be cooled very, very slowly, because any cracks would make it impossible to make a telescope out of it. So it's annealed or cooled over a year. And during that year, that mirror blank broke. It failed. Corning had to pour an entirely new one and wait another year for it to cool before shipping it to California, where it took 10 years to grind the glass down to the correct shape for the Palomar telescope. So the Palomar telescope actually got first light 2 months and 2 days after I had my own first light. That is 2 months and 2 days after I was born. Now, in March of this year, driving up to Corning, I went to the Corning Glass Museum, and there is that original mirror blank, which failed and is cracked, hanging vertically inside their most glorious glass museum in the world. They've got glass going back 4,000 years. It's a spectacular museum. But there sits the mirror, and I had forgotten that they had kept that. I went to the museum to see the glass, and so this was a real treat for me to discover there sits that original mirror blank for what was the world's largest telescope, the Palomar telescope in California. Telescopes I've used since then, well, here's the Japanese Subaru telescope with an 8-meter diameter mirror, substantially bigger than the Palomar telescope. We put our observatories in very remote, supposedly dry places. This particular observatory is on a mountaintop in the northern hemisphere, and this picture I took when I was observing with it recently. I took this picture in the month of June, and of course, June in the northern hemisphere is summer, and there's snow. And so you might ask yourself, where does it snow in the middle of summer? And the answer is Hawaii. This is on top of Mauna Kea on the big island of Hawaii at 4,200 meters above sea level. We're above a good part of the atmosphere. We're above the atmospheric moisture and water vapor, where the seeing is absolutely outstanding, and the air is very stable. So the Hawaiian mountaintop on the big island is one of the world's best observing sites. That's the Subaru 8-meter telescope. The other 8-meter telescopes I've used are the very large telescopes in Chile. There are 4 of them, each with 8-meter diameter mirrors. They can be used as a single telescope, and when that happens, they're then the world's biggest telescope. But that's unusual. That's a very expensive thing to do. I've only ever used one at a time, the second one that you see right here. And during the day, I can walk in under the telescope, stand next to the instrumentation. You can now see how big this telescope is, phenomenally big. But I think this is going to disappoint you a little bit. No human being can look through that telescope. There is no eyepiece. Astronomy doesn't work that way anymore. And there's a good reason for that. There's several good reasons. One is, I mean, there I am standing next to it, but if it were nighttime, it would be dark. The lights would be out. That's a big, dangerous machine. That wouldn't be safe for me. And worse yet, I've got body heat, and the heat from my body would cause the air to shimmer and actually degrade the observation some. More importantly, those telescopes cost about $50,000 US per night to operate. And with that extreme expense and the fact that you're paying your tax dollars, your tax pounds, you're supporting us astronomers, we're not going to waste the telescope time that you're paying for by looking through it with our eye because it's fun. We've got that light going to our instruments, so we're getting the maximum scientific return from the telescope. We actually do the observations now rather less romantically, not sitting in a cage up at the prime focus, but sitting around banks of computers that control the telescope, with a professional operator over here who operates the telescope. That's a $200 million machine, and they're not going to let the likes of me drive it in case I crash it and damage it, with other astronomers operating the computers, protecting those from me too. And when I'm the observer, I'm the one who's decided what the program is. I've loaded up the programs necessary for everybody else to run to get the observations that I've been given time to do. There was even one time when I had 3 nights simultaneously on the Very Large Telescope in Chile and the Subaru telescope in Hawaii. I sent my student to Hawaii. I went to Chile for that, where we made simultaneous observations for 3 nights on an object with some great discoveries from our point of view. Just for fun, from that observatory, we're now looking down on the residencia where the astronomers, the technicians stay down here. And this is just to show you, this is one of the world's driest deserts, the Atacama Desert. And it basically doesn't rain there. It looks like the surface of Mars. And so we've built bigger and bigger telescopes, and we've moved them to more and more remote sites. We're away from all lights from human beings, and where we're above the atmosphere. This is 2,400 meters above sea level, so that the clarity and the seeing is better, and so that it's extremely dry and almost all nights are clear and we can do the astronomy. This residencia, by the way, did appear in a James Bond film some years ago, Quantum of Solace, where the end of the film finished with a great battle between him and the bad guys here in the residencia. In the film, this was blown to bits. Of course, that was done in a studio. Didn't actually happen to the observatory. 2 gigantic telescopes on Mauna Kea in Hawaii are the Keck telescopes, funded by a person named Keck, a philanthropist. They are 10-meter diameter telescopes, and they have got a novel technology, at least when they were first built. The idea came from, let us say, bees. We know how bees build honeycombs and how hexagons fit together so nicely. And so the mirror of the Keck telescopes is a series of independent hexagonal mirrors that are placed next to each other. Now, in 1979, I went to an American Astronomical Society meeting in Mexico City. And when I landed at the airport, I got the airport bus into town. I was sitting in the very back seat, and there was another young astronomer sitting next to me. His name was Jerry Nelson. And I asked him what he was doing, and he said he was coming to present an idea he had to build giant telescopes, not with a single large mirror, but using many, many mirrors put together, and then using edge sensors, devices that could actually position those mirrors and hold them in place perfectly to a precision of about 10 billionths of a meter, 10 nanometers. The technology had developed to where it was possible to use multiple smaller mirrors and keep them all exactly in place to less than the wavelength of light. Well, Jerry Nelson is the one who built those telescopes. It was the only time I ever met him. His story to me sounded fantastic. Nobody had ever done it before. So I was amazed by his story, but didn't at the time actually realize he would accomplish what he set out to accomplish. And now big telescopes, lots of them are built with this pattern of many mirrors that are put together like this and held in place by incredibly precise technology. Now, using those Keck telescopes, Andrei Getz, UCLA, Reinhard Genzel, using the 3.5-meter new technology telescope in Chile, both won the Nobel Prize in Physics in 2020 for showing that there's a black hole at the center of our galaxy with 5 million times the mass of the sun. They needed the giant telescopes to do that. Now, they worked in the infrared. I'm not mostly talking about infrared now, but the infrared allows you to see through the dust of the galaxy. The dust blocks our view in the visible. So they could see through the dust 30,000 light years away to the center of our galaxy. And there they measured the speeds of the stars, and the stars were moving about something at incredibly high speed, meaning there's a lot of gravity, and that thing was tiny and invisible. And here from the European Southern Observatory is a computer animation of the positions of those stars as measured by Reinhardt and by Andrea. Going year by year, down in the lower left corner, the orbits are mapped out. But the positions of the stars are real. This is what they measured. The gas cloud has been put in figuratively just to show that a gas cloud coming close to that central black hole gets stripped and the black hole eats the gas and it grows bigger. That's how the black hole has grown to be such incredible size. This is now predicting in the future where those stars will be, and the observations are ongoing. And so again, our ability to see to the center of the galaxy, and in this resolution, we need the giant telescope to have the angular resolution. It's another driving reason for giant telescopes. Currently, the biggest single telescope on the planet is the 10.4-meter diameter Gran Telescopio Canarias, the GTC. And just to show you something of the technology, it's also got hexagonal mirrors. But I was a lecturer in a winter school for graduate students in 2010, and we went over to La Palma, the island where this telescope is, and we took our students with us, and then we gave them the chance to push the telescope around. It weighs 400 tons, and it floats on a thin layer of hydraulic oil, and it is so finely balanced and so frictionless that here, this was my graduate student, Kelly Hamilton. She's now a professor at Villanova University in Pennsylvania. She and a couple of the other students are actually rotating this 400-ton telescope with sheer muscle power because the technology is so good and things are so perfectly balanced. Now, there's a new telescope right now just coming online. It's called the Vera Rubin telescope. It's in Chile, and it has an 8.4 meter diameter mirror. This is Vera Rubin herself, 1928 to 2016. She is a very famous astronomer. She did her undergraduate degree at Vassar College, and then in 1948, she wanted to do her PhD at Princeton, and Princeton said, no, go away, we don't take women. And Princeton did not actually allow women to study astronomy until 1975. I was already finishing my PhD by that time, so women in my cohort could not actually do their PhDs at the likes of Princeton at the time I was doing my PhD. They could in Texas where I was. Vera Rubin essentially found the proof of dark matter. Dark matter had been surmised by Fritz Zwicky, working with that 2.5 meter Mount Wilson telescope in the 1930s. But what Vera Rubin did was she measured the velocities of stars. This is the great galaxy in Andromeda. And she's measuring the velocity of the stars as they orbit this galaxy. And we know what the laws of orbits are. Johannes Kepler discovered those in the 1600s. And so here is a map of how fast the stars are moving and how far away they are from the center of the galaxy. And when the stars stop, when almost all the mass is inside, these velocities should just drop. That's what happens in the solar system with the planets orbiting the sun. They should go slower and slower and slower. They don't, not just for Andromeda, but for other galaxies too. The velocities remain up. And from that, Vera Rubin deduced that there was what she called missing mass, we now call dark matter. This is the big evidence that galaxies are primarily made out, 95% made out of dark matter, and we don't even know what it is. And so she probably should have got a Nobel Prize for that. She didn't, probably because she's a woman, but she certainly had many, many awards in her life. And now this new telescope, the Vera Rubin Observatory, named after her, it's a nighttime picture of it in Chile as it looks now, and it's coming online. It has got a 3,200 megapixel camera. Your camera in your phone, if you got a good phone, maybe you've got a 50 megapixel, 48 megapixel camera. It's one 3,200 megapixels. And this telescope, here are the facts. I just want to tell you about this. It's taken 30 years to complete it. Giant telescope, 8.4 meter diameter. Its field of view is 45 times the diameter of the full moon, 10 square degrees. This giant camera of 3,200 megapixels, it's going to take 1,000 images of the sky every night for 10 years. It's going to image the entire southern sky, the whole sky down to incredibly faint brightnesses every 3 nights for 10 decades, for 10 years. Amount of data gathered, 20 terabytes per night. I'm giving you this presentation on a very high-end MacBook Pro computer on which I've got 1 terabyte of storage. This very expensive computer, I would need 20 of these computers to store the data from one night from that telescope. And so all the data are being searched by artificial intelligence. You're hearing about AI in many things now in life. It's in the news all the time. But in terms of data analysis, astronomy is a big driver of artificial intelligence. We astronomers can't just go look at the pictures anymore and discover what's there. We need the computers to do that for us. Look at what's expected. 10 million alerts per night. These alerts are for things that have changed in brightness, things that might be doing something really interesting. 10 million per night. Just here, the Rubin telescope will discover 10 million supernovae. Now, supernovae are stars that explode. They're a fundamental way we measure distance in the universe to get the age of the universe, to look back into time. And I have a friend, Tom Bowles, who's the person who discovered the most supernovae of any human ever. Tom Bowles discovered 149 supernovae over his entire life. 149. This telescope will discover 1 million per year. This is a complete game changer. Astronomy will be revolutionized starting next month. In just a few weeks' time, we get first light from the Rubin telescope. June 23rd, it should be in the news. Keep an eye on it. The discoveries should just come pouring in. And over the next decade, much of astronomy is going to be driven and guided by what this telescope does. Last topic for tonight, and then the giant telescope of all giant telescopes, is adaptive optics. This is a laser beam shooting into the sky out of a telescope in Chile. We can now make mirrors which are very thin. They can't support themselves completely under gravity, so they're supported by supports behind them and actuators, and they can be bent and distorted so that when the light comes in through the atmosphere blurs the light. We call that seeing, and it makes the images a bit blurry. It's why the Hubble telescope gives such sharp images. It's above the atmosphere. But if there's a bright star in the field, a telescope like this can image that bright star, and knowing that it should be a point and seeing that it's blurry, you can use computer technology now and actually determine what the atmosphere has done to blur it and bend the mirror with actuators underneath it to correct for the blurring of the atmosphere. Now, the atmosphere changes so fast, you need to do that 1,000 times per second. We can do that. The technology is there. The actuators, the measurements can be done on a millisecond time scale. The actuators can bend the mirror and distort it and change it so that we can get space-based resolution from the ground. And of course, the resolution then is vastly better than from the Hubble Space Telescope, because the telescope's on the ground, the mirrors are so much bigger. The bigger the mirror, the better the resolution. Now, often when you're looking at the sky, there is no bright star to use for this adaptive optics. And so in this case, you fire a laser which has got the wavelength of sodium light. And there is sodium floating high in the atmosphere, about 20 kilometers up. A lot of it comes in micrometeorite dust. And the laser beam causes the sodium to glow, and it creates an artificial star in the sky, which can be used in any pointing, anywhere you're looking in the sky. A few years ago, the top of this mountain in Chile was blasted off. It was 3,064 meters high. 18 meters were blasted off the top. And on the flattened top of that mountain is the biggest telescope in the world under construction now. It'll come online in 2027. It is the European Extremely Large Telescope. There's an artist's impression, multiple laser beams shooting out for the adaptive optics. Mirror diameter, 39 meters, but that 39-meter mirror is made up of many, many small segments. Here's an artist's impression of that telescope with, just for scale, Big Ben next to it. So many of you are in England, you're in the Lincoln area, you know London well. Almost all of you have at least seen pictures of Big Ben if you don't know it. There it is, 90 meters high. And of course, this telescope rivals the height of Big Ben. Here's the facts. ELT, this is really big glass. The telescope's nearly 1.5 billion euros for construction, 39-meter diameter, but it's not a single mirror. It has 798 1.5-meter mirror segments. Now, let me take you back. 1908, George Ellery Hale completed the world's biggest telescope, a reflecting telescope on Mount Wilson. And that telescope had one mirror, 1.5 meter in diameter. This telescope has 798 mirrors, the size of Hale's biggest telescope in the world only slightly more than a century ago. The edge sensors keep the mirrors positioned to 10 billionths of a meter. The mirrors are polished to that precision. There are 4 more mirrors to send the light to various instruments, and one of them is the adaptive optics mirror, and it's incredible technology. So that adaptive optics mirror, here's a picture of it. It's 2.4 meters in diameter. It's made of 6 individual shells, only 2 millimeters thick, with 5,000 actuators that can bend the mirror and cause it to distort perfectly to accommodate the distortions in the Earth's atmosphere, to give this telescope diffraction limited, we call it, resolution as good as it would have, or nearly as good as it would have, if we could put it into space, which obviously is absolutely impossible for something as big as this. We haven't got the rocket power to launch this sort of thing into space. So that is the European Extremely Large Telescope, coming online 2027. Its main science focus areas are almost everything in astronomy. It'll find thousands of new objects in the solar system. It'll study exoplanets around other stars. We'll look at stars like we've not seen them before, black holes closer up, galaxies in great detail, the problems of dark matter, origin of the universe, fundamental physics, and of course, anytime you can look more precisely at the universe, there are going to be unexpected discoveries. Now here, next to last slide, is a comparison of telescopes, and I need my cursor. I hope you can see my red arrow. Up in the left corner, that little blue dot is the size of the Yerkes 1 meter, the world's biggest refractor, built by George Ellery Hale. Down here is the size of the California telescopes, the Hooker telescope that he built, and then the 5 meter, 200-inch telescope, the Palomar telescope. Over here is the European Extremely Large Telescope, the ELT. There are other giant telescopes planned. This is the big one coming online in 2027. But look where we were a century ago. And even more, look where we were when we started. Those are the tiny little telescopes held by hand with which Isaac Newton expanded our view of the universe by seeing phases of Venus, moons of Jupiter, stars like nobody had ever seen before. And now we are building some of the most complex, sophisticated, technologically advanced machines that humans have ever built to see deeper and deeper into the universe and to expand our human understanding of our place in the universe more deeply. Okay, thanks for your attention this evening. I hope I've left a little bit of time for us to have some questions now. There, I'll stop sharing, and here I am again.
Thank you very much, Don, for this wonderful talk. We are now open for questions, which you can type inside of live chat, please. And we will run somewhat longer so that you can ask your questions. However, I first ask you, if you did enjoy Don's talk, please push a like button under the video, which will help more people to see it. And I see some questions which already came. So AC is asking, will the extra large telescope able finally see some Oort objects?
Will the extremely, oh, sorry, AC, hello from San Diego for you. I realize that's where you are. That's a good question. Sorry, for the rest of you, the question is about the Oort cloud. The Oort cloud is a cloud around the sun, way out beyond Pluto, that we can tell houses probably trillions of objects the size of comets, because that's where comets come from. Of course, AC, it will be able to resolve the Kuiper belt objects, the small things that are Pluto-sized. I need to do that calculation, AC. It's not too difficult to do, given that it's 39 meters. We just have to make an estimate if it were, say, something the size of Halley's Comet, and if Halley's Comet were just beyond the Kuiper belt. I'm not sure, AC. I'll do that calculation when we go offline here and see what the answer to that is. It's not too difficult to do if you'd like to try it yourself. The resolution just goes as telescope aperture. In fact, that formula was there for you earlier in the talk.
Thank you, Don. Yeah, Rayleigh criterion formula was there. I see question from Martin Cook. What may be the chance of adaptive technology on a lunar telescope?
Oh, Martin, if we went to the moon, we wouldn't need the adaptive technology in order to remove the blur of the atmosphere, because the moon doesn't have any atmosphere. And so the need for it there would be less. But part of that technology is being able to change the shape of the telescope mirror very, very rapidly. And one of the reasons we need to do that is called tip tilt. When the telescope moves across the sky and it changes its orientation, the gravitational pull on those mirrors is changing. And that, if you do nothing, can distort the mirrors. And so the telescope, the adaptive optics, the actuators are in real time, always correcting for the tip and the tilt of the mirror because of the change of gravity on them. That will be less of a problem on the moon with lower gravity, but it will still be a problem. So that technology will be transferred to telescopes on the moon. We'll still be able to use very, very thin mirrors. That's important. You need them to be light. It costs a lot of money to send things up. And then you can use that technology, but you won't need it to correct for distortion from the atmosphere because there is no atmosphere.
Thank you, Don. There is another question/comment from AC. No matter how far away and remote the telescope is built today, it is impossible to avoid the scourge of the Starlink sky pollution. Is it really a big problem, Don?
The answer is thank you for that comment, AC. As you'll see that normally my Astro-Chats are not as long as this one, and I chose not to say something about that simply because I was going along so long. I'm really pleased that you asked it. Starlink and its cohort, the one Jeff Bezos is putting up, they are going to be putting up satellites by the tens of thousands in low Earth orbit. Collisions between these satellites, low Earth debris, safety of low Earth orbit is a major concern. But as astronomers, the Vera Rubin telescope in the early evening is going to be streaked with images of these satellites all over. And astronomers are already developing the technology to try to use computers to remove those streaks or at least extract data around them. But it will be a major problem for astronomy. We no longer have a pristine night sky that isn't going to be streaked with satellites by their tens of thousands. Now, you and I probably for other reasons want those satellites for communications. Though you can forget about fiber optics even. With those satellite clusters, you can have cell phone communications, internet communication across the entire planet to everybody on the planet. You don't have to be in some place that's rich enough to be able to put wires in. Everybody will be able to access it ultimately. So for communication, that seems like a good thing. The companies building them understand that they're a problem for astronomy. And so they are trying to paint them in such a way that they're very low reflective and not reflecting too much sunlight. There's making some effort to ameliorate the problem, but they can't make it go away. And with telescopes as powerful as the Vera Rubin telescope, in the early evening and the early morning when the sun's reflecting off those low Earth satellites, the images will be streaked. And we will have to deal with that, but it will degrade our observations beyond what they would have been if all those satellites weren't up there. It's a competition between technology and our style of life and our desire to look at the sky. And you've seen that problem. I'm going to go on about that. You've seen that problem already. Most of you probably live in big cities, and you don't ever get to see the sky the way I do when I just step out of town here in South Africa into the dark, where it's so dark I can not only see the Milky Way, which goes right overhead, I can see my shadow by the Milky Way. That's gone for most people on the Earth too. Astronomy is not as good as it used to be because of our technology. We want these things. It's one of the prices we pay.
Thank you, Don. I wanted to ask a question. Actually, you mentioned that with a new telescope coming, amount of data will be tremendous today, and artificial intelligence already helping. Can you just illuminate a little bit more? What kind of role of artificial intelligence right now in astronomical research?
Yes, Andrei, in astronomical research, we normally have just called this machine learning. And so we teach the computer how to identify things, say in a picture of the sky, that we can do with our eye, but it's time consuming. And so the discovery of a supernova, for example, a star, since last night, when you see it again tomorrow night, has gotten much brighter. And the next night, it's much brighter. And so there's a light curve of extreme brightening very rapidly. The way those were discovered from the ground were people like Tom Bowles knew the sky so well that he would look through his little telescope by eye and say, "Whoa, there's a star that wasn't there last night," because he knew all the stars. And so he discovered 149 supernovae that way. We can teach the machines to look at the picture and to flag up everything that's changed in brightness, and then over time to draw a plot of the brightness versus time. And we know what those curves look like for supernovae. And we teach the computer, if you see a light curve like that, it's a supernova. If you see a light curve that looks like one of the stars I work on that oscillates and vibrates, then that light curve will tell you it's a star of interest to me, and the computer can identify that and tell me, hey, look, in your lifetime, you discovered dozens of these things. I just found 500 of them tonight. Do you want to look? And so the computer will do that job by identifying what the change in brightness looks like compared to what we've seen before. And we've trained the computer on the light curves of what we've already observed. We call it machine learning, but it's the same as artificial intelligence.
Okay, thank you. There is a question from Martin Cook. We have a picture of black hole. How about a sharp image of an exoplanet?
Martin, even the European Extremely Large Telescope is not going to give you an image of an exoplanet. They are too far away and too tiny. It won't even be coming close to the resolution needed for that. It will have the resolution to resolve closer stars. We can already do that with our big telescopes. So that, for example, Betelgeuse, which is a supergiant star, if you put it where the sun is, Betelgeuse would stretch out to Jupiter. And with our biggest telescopes, we can resolve the surface of Betelgeuse into several pixels, a few. A planet, the Earth is 1/100th the diameter of the sun. It's 1/500th the diameter of Betelgeuse. There's no way that we will resolve the planet. But what the telescope will be able to do is separate the planet from the star. That angle will be big enough that the telescope can look at just the planet and take spectra of it. And from the spectrum, we can tell what the atmosphere is made out of, and we can look for signs of life in the atmosphere. That's being done already. The European Extremely Large Telescope will make that possible to do for many, many more exoplanets.
Okay, thank you. Question from Timur. Has there been any research in any other transparent material to use for lenses other than glass, which was mentioned to be not suitable for very large lenses?
Well, Timur, I made a very simple statement when I said that the kinds of glasses that are used for making those large telescopes are very special glasses. And the answer is that sort of research into different kinds of glasses for optical purposes, not just for telescopes, for lasers, for example, for anything that uses a transparent material for light passing through it, that sort of research is extremely deep and well done with many, many materials. That doesn't mean that all possible materials have been discovered, but if you actually would, instead of being a mathematician, if you think in your life you would like to study materials for better optical transmission, there's a great career out there for you in that.
Okay, thank you. AC is asking, do you think a Mercury pool or maybe gallium mirror telescope will ever be built?
AC, that's been done. There's a Canadian astronomer named Ermanno Borra, B-O-R-R-A, and he built Mercury mirror telescopes. Now, what he does is he has I don't know, but they're big. They're a couple meters across. They may be 3 meters across for his telescopes. And he spins them. And when he spins them, the Mercury will then settle into a perfect parabolic shape, which is the shape that you need to focus the light and make a mirror. And he's done that. Of course, the telescope can only point straight up. You can't tip it anywhere, otherwise the Mercury runs off. But there are radio telescopes like that too. You simply wait until an object comes into view and you move the secondary mirror, and you can do astronomy that way. You must isolate a Mercury mirror telescope completely from all possible vibrations. And in the modern technological world, I think Ermanno Borra was building his telescopes up in British Columbia, cars driving on roads, maybe even a football game nearby in a stadium with the fans jumping up and down and yelling, planes flying over. The vibrations are a real problem. It's hard to get to an isolated environment where you're getting no vibrations to distort your Mercury mirror. But if you'd like to look that up, if you look up Ermanno Borra, B-O-R-R-A, and Mercury mirror telescopes, he did build them and he successfully made observations with them. That has been done. It's an interesting idea because you get the parabola for free when you spin it. And as long as I'm on that, I did my master's thesis with a man named Paul Vandenbout, who became the director of the U.S. National Observatory, and another man named Roger Angel. And Roger Angel went into building giant mirrors, and he builds 8-meter mirrors underneath the football stadium at Arizona, University of Arizona. He has a big mirror laboratory there. And when he makes the mirror, unlike Corning, when they made the mirror for the 200-inch 5-meter telescope, it took 10 years to grind away 4 tons of glass to make the paraboloid. Roger spins his 8-meter mirrors as they're cooling. And so when they cool already into a paraboloid, and then the necessity, they need to be finely finished so that they're perfect to a fraction of the wavelength of light. But the amount of glass that needs to be ground away is tiny compared to what it used to be. And he's a big manufacturer of some of the world's 8-meter telescopes using that technology of spinning a liquid, but in this case, a glass which over time cools and solidifies.
I see there is a comment also from from San Diego. I see the Falcon launches with Starlink from Waldenburg all the time. Kind of sad.
Yeah. For us looking as astronomers, the pristine sky is gone, and that's going to get much, much, much worse.
Don, just a question, and what about large telescopes in another kind of countries, not only kind of US or Europe? Is any development in China, for instance, in that regard?
Andrei, first of all, the world's biggest telescopes are in Chile.
Mm-hmm.
Look, what we're looking for a desert environment with very fine conditions. And it turns out the world's best sites for observatories tend to be on mountain ranges, close to an ocean, and frequently on west coasts. And so there's your California observatories, your Chile observatory. There's your single observatory, Mauna Kea. The Chinese have built big telescopes, yes, and they've got big mountains. The Indians have got, they've got an optical telescope at 5,000 meters, which is so high you have to operate it remotely because humans don't function very well at 5,000 meters. There are observatories in Kazakhstan, in Uzbekistan. In Africa, our best observatories here are South Africa because we've got some nice mountains on the west coast overlooking a stable ocean environment. Australia, you've got observatories on both coasts. So Southern Hemisphere, the only good land we've got for observatories is Chile, South Africa, and Australia. Northern Hemisphere, there's a lot more land and their choices, but you need to be in desert environments and away from human habitation. When you go for radio observatories, this all changes because radio observatories, we're not worried about the weather, and we're not quite so worried about human habitation, although we are when we get to something like the square kilometer array. That's largely being built in South Africa and in Australia. And here in South Africa, the square kilometer array, and I will put that telescope in the next Astro-Chat. That will be, radio telescopes will be a topic for that next Astro-Chat. If you go to visit that observatory, you have to go by appointment. You go to the headquarters, and then you're driven tens of kilometers off into the dry area where the telescope is. You may not take your cell phone with you. You check that at the door, because even in the off position, it's emitting radio waves that telescope can see and would be disturbing its observations. So you can't even carry an off telephone into the vicinity of the telescope. And so the reason for the telescope being built in that part of South Africa and in the northwest of Australia is looking for a radio quiet environment that's as far away from human beings as possible. The ultimate place for that, question we just had earlier for optical telescopes, the best place for a radio telescope, the other side of the moon. If you go to the far side of the moon where the Earth is invisible, then you're not going to pick up the radio waves that we beam out here on Earth. That's the ideal place to go put a big radio telescope. Not just space around the Earth, you've got to worry about radio emissions from the Earth. Boy, we talk to our satellites. Get to the other side of the moon and the moon blocks the Earth from your view. That's the place to go. That's probably a good place to stop too, Andrei.
Thank you. Thank you very much. thank you everyone who visited us this night and asked questions. We will send you email asking for your feedback. Please do spend a bit of time to write in it. It'll help other people to find this video. And while you're still here, just click on this symbol, like button, which will also help other viewers on YouTube find this video and watch it, its recording. And with that, I'll thank everyone who came and spent time with us. I thank also Don for talking to us from South Africa.
My pleasure.
And I hope we will meet again and talk about other fascinating topics in not too distant future. Thank you very much, and good evening, good night, and good morning.
Yes. Okay. Bye, everybody.